Good morning, physics students, and welcome to another episode of Physics. It's Mr. Finn coming at you from neighborly Northville. Hey guys, today we have the Google form for the week on series and parallel circuits. Now remember, that's not including the compound circuits. Compound circuits is what we're doing today on the video, and we did yesterday. But today's Google form, end of the week Google form, is just on series and just on parallel. So when you guys get a chance to do that later today, make sure that you are just studying series and parallel independently. And remember, those rules were on page 552 and 553 of your textbook, so you should have a pretty good way of reviewing that. Also the lab, the simulation lab, the introduction to circuit lab, which was available Wednesday. Make sure you guys get a chance to finish that up at some point. Get that into me. I'd like to get those scores recorded, and hopefully we can get set up for the next lab coming early next week. So hopefully you're finding that easy to get to the simulation and run through. Okay guys, today in a compound circuit I'm going to show you a little bit different situation than we had yesterday. I'm going to show you a series shell with parallel mixed in. So you need to run through these videos a little bit more, or you need to pause and move back. These are a little bit tricky, so make sure you get some time on task. Let's go ahead and look at today's circuit. Okay guys, let's check out what we have today. We have a 6-volt supply, and what you can see in this particular video, or this particular example, is we have an R3 located in the branch where there's only one way to go. You'll recall from our discussion on series that when we draw this current, there's only one way for that blue current to go. We're going to call that current total. So the R3 resistor is in the line where current total exists. Then what happens is the current splits. Now what we're going to do is we're going to draw point A and point B a little bit differently than we have in the past. We are going to separate that parallel section between A and B. I'm going to draw a green line representing current over the top branch, and I'm going to draw a pink line representing current from the lower branch. Now hopefully you guys remember that the pink current and the green current, they should add up to the total current, because in parallel, branch currents add up to the total. And we're only splitting one point. We're splitting at point A, and we're getting back together again at point B. So what is our way of solving? One of the ways that we want to make sure we do this consistently is we reduce resistors. We have a combination circuit. We're going to choose to reduce resistors right away. And we're going to do that by a redraw. Now before we get into the redraw, let's take a look at what we're looking at here. A little bit different than what we saw yesterday. I want an equivalent resistor of 1 and 2. I want the total resistance, the voltage across R3, the voltage across the equivalent resistor, and then the currents through R1 and R2. So it's a little bit different than what we asked last time. I also have my redraw up here, which I'm going to work from now. Notice that we've blended R1 and R2 into one equivalent resistor called Req. And we did this yesterday, so let's figure out how to do this. I have these two resistors. How are they wired? They're wired in parallel. So I can simply do 2 times 6 over 2 plus 6 to give you 12 over 8, or 1.5 ohms. So this equivalent resistor is 1.5 ohms. That's my resistor reduction method in parallel. So 1.5 ohms is going to be right here. Now the redraw means if I took the 6 and the 2 out and I placed an equivalent resistor in its place that electrically did the exact same job, it would be a 1.5 ohm resistor. Now you can see that This circuit that's redrawn is actually a series all the way around. So we've done our job. We have reduced resistors until we got only one value, either all parallel or all series. It just happens to be all series. From that, we can find our resistance total. Remember, in series, we can simply add all those resistors up. So what's 1.5 and 0.5? That's a total resistance of 2.0 ohms. 2 ohms. Okay, guys, we're making some progress here. Now here's where it gets challenging. Voltages. Where are we going to find those voltages? In order to find applied voltages, we have to find the current in the circuit through the resistor. Well, I don't have a current yet. I don't know what the blue current is, but I can find it out because I've got a total resistance of 2 ohms and I have a total voltage of 6 volts. Therefore, 6 volts divided by 2 ohms gives me 3 amps. 3 amps is the total current in blue. My total current is 3 amps. It's also the same current that goes through resistor 3 because resistor 3 is in the single branch. So what would my voltage across R3 be? The current that goes through it, 3 amps times the resistor's value, 0.5 ohms, to give you 1.5 volts. 1.5 volts applies just to resistor 3. Now guys, if you remember, when I measure voltage, I simply take my voltmeter and press it across the bulbs. So if I did that with my voltmeter, which is this object, simply measuring voltage, and placing these 2 leads on either side of the bulb, I would read 1.5 volts. Now you guys might also remember that in series, voltages have to add together to give you the total. So, working with our redraw, if I know that this is 1.5 volts, and I know my total is 6 volts, then how many volts should be impressed across the equivalent resistor? How many volts are left to plug across that resistor? The answer is 4.5 volts. Because 4.5 volts and 1.5 volts equals 6 volts. Now I could also solve that later. If I knew the current through this resistor, couldn't I multiply by the value of 1.5 ohms? We do, and in this drawing, it's blue. It's a total current. So I could actually say 3 amps times 1.5 ohms to give you 4.5 volts. So I can solve that using Ohm's law. Now guys, the last part is how much current goes through R1 and R2. Well, what we know is the voltage across this branch happens to be 4.5 ohms, 4.5 volts rather. And we know because it's parallel, it's got to be the same across both branches once I determine what that actually is. So, by determining 4.5 volts from here to here, by the way, in this drawing, A to B is across that equivalent resistor. So voltage AB is 4.5 volts. The same as the voltage across the equivalent resistor is the same across both of these resistors because they're in parallel. In parallel, to find the current, we applied Ohm's law separately to each branch. So that's what we're going to do. We're going to take the 4.5 volts and divide by the 2 ohms for R1 to give you 2.25 amps. That would be the green current, 2.25. I wonder what the pink current would be. Well, it would still be 4.5 volts because that's the voltage applied to that section. If I divide it by the 6 ohms, remember I'm applying Ohm's law separately to each branch, I'm going to get 0.75 amps. Now how do we know if we've done this correct? Remember guys, parallel branches must have currents that add together to give you the total. So if I've solved for 2.25 amps here and 0.75 amps pink, then shouldn't it be that the pink line and the green line add together to give me the total? 2.25 amps plus 0.75 amps gives me 3 amps total. It looks like we've done that right. Guys, I'm going to need you to work through this again with your paper and pencil and make sure that you can solve combination circuit, this time with a series shell and a parallel portion mixed in. What did we do first? We reduced resistors to find all series. Then we found the current in total. We used that current to find the voltages applied to the branches when branches were reinserted. It's kind of tricky. We're going to go over a couple more of these next week, but I really need you guys to go through your homework questions and make sure that you can perform this function accurately. Okay guys, you have your Google form today on parallel and series circuits. Next week we'll continue with 2 more examples of compound circuits, and I'm going to let you guys watch that video from Crash Course Physics on circuitry. And then that should do it for compound circuits and all of circuits together. But it's going to need your attention at the beginning of next week. Don't forget to get those labs into me, guys. And let's have a great weekend today, or this weekend. Okay, guys, to wrap up, please take the time and go through those videos as carefully as you need to. Compound circuits can be tough, but we'll just take a few to make sure that you guys are good. And then we'll be able to move on to magnetism. But I'm hoping you guys are okay, and we'll see you at the Google Meets. And good luck on today's Google form on series and parallel circuits. Okay? Take care.